Alright, welcome everyone, and I hope you guys are doing good. Now, before I start talking about this problem, let me tell you guys something. Summer is coming, and where I live in the Punjab region of Pakistan, and it gets really hot. It gets really hot, and by hot I mean over 40 degrees Celsius. Calculate how much that is in Fahrenheit. That's your homework. Alright, now I'm just kidding. So one of the measures to keep your house slightly cooler in warm temperatures is the double-pane window. The double-pane window. Okay, and that's what this problem is dedicated to. Double-pane window. And we're talking about just a single double-pane window. And once we've had our discussion on a single double-pane window, then you can just go ahead, hopefully go in the real world and maybe have a better understanding of how this works. Okay, so this is gonna be a 3-part problem. Okay, I'm gonna solve this problem in 3 separate parts. Okay, right now I'm gonna ask you to pause the video and read through the problem. Pause now. Okay, I'm assuming you've given it a read yourself. Now let's read it together. A double-pane window, okay, that's what we're talking about, is shown in figure... Oops, my bad. I said figure 1. It was supposed to be figure X. My bad. That's on me. Sorry. Now, air... Alright, moving ahead. That's my figure right here. Okay. Air is trapped between 2 flat sheets, okay? Let's make it flat sheets of glass, because usually, like, I've yet to see some curved windows. It's usually flat windows. The air gap is so small that there can be no bulk motion. No bulk motion? What does that mean? Okay, we're gonna deconstruct that in a bit. The gap and each sheet have, sorry for my grammar, English is my third language, sorry, have equal thickness. Okay, so this right here is L1, this thickness right here is L1, this thickness right here is L, and this thickness right here is also L. Alright, equal thickness. Very good. Assume perfect contacts. Okay, these are some points that we're gonna discuss. Okay, hold up, sorry. These are some points that we have to discuss. And yeah, you're asked to find the steady state. You're asked to find the steady state temperature profile. That's our main objective. And the other info, you've been given the conductivity of air, the conductivity of glass, and the temperatures at x equals 0, which is the outside wall, here. And temperature at x equals 3L, which is the inside wall, the edge of the inside wall facing your room, the face. Okay. With that said, can we start solving this problem? All right. In the first part of this video, I'm just gonna formulate this problem. All right, in terms of the governing equations. Let me just copy this and paste it down again, and we're gonna play with it a little. And we're gonna have some fun. All right, so now in this problem, okay, I have 3 domains. All right, I have the outside glass. Give me a second. I have the oh, my bad, sorry. Get rid of that. I have my outside glass. My outside glass, quote unquote. I have my air gap, quote unquote, air gap, and I have my inside glass. All right, and there's going to be an equation, there's going to be a governing equation for each of these domains. So I have a total of 3 domains. Excuse me. So I have a total of 3 domains. And I'll have to write the equation for each domain. Okay, I'm going to designate the outside glass as domain 1, domain uno. Domain dos, the second domain is the air gap, and the third domain is the inside glass. Let's just let me just switch colors to make it more appealing. All right, the aesthetics. We live for the aesthetics. All right. Now with that said, all right, let's see. We need a governing equation for each of these. So we assumed, let me rewrite my assumptions. Let me relist my assumptions. Steady state, of course. Steady state, that's going to make our life so much easier. Constant conductivity, that's a good one. That's going to make life easier. Constant conductivity. What else? We said perfect. We said no bulk motion. No bulk motion means, what does no bulk motion mean for our heat transfer problem? It means that we only have conduction. Conduction only. That makes life so much easier. Conduction is one-dimensional conduction is easy to handle. Okay, one-dimensional conduction is easy to handle. And next up we have perfect contacts. I'm going to talk about perfect contacts in a bit. All right, perfect contacts. I'm going to talk about that in a bit. So for my first domain, domain 1, my governing partial differential equation is going to be the row of glass, the heat capacity of glass, times the rate of change of temperature with respect to time is equal to the conductivity of glass times the Laplacian of the temperature. Oops, this is the temperature in glass in domain 1, hence I'm designating it as T sub 1. Okay, T sub 1, this is the domain. This designates the domain of that equation. All right, and I know that I'm operating at steady state. Operating at steady state means that I get rid of the left hand side. Steady state, bye-bye. All right, well done. And so in vector form, this is my governing equation, my simplified governing equation in vector form. Note I have divided both sides by kg, k sub g. That means that I can just get rid of it. Okay. All right, so now I have my governing equation in the vector form. This is a partial differential equation, but I want to reduce it to an ordinary differential equation. So I'm going to make it more explicit. The second derivative with respect to x, the second derivative with respect to y. You guys know the drill. The second derivative with respect to z. You guys know the drill. Make sure I don't make any algebraic mistake. That's gonna make me lose a lot of points on this problem, and I hopefully don't want that. And we're also, one of the assumptions that I should also list out here, one directional transport. That is important. All right, one directional transport. The heat is being transferred in the x direction. Okay, let me make the coordinate system a bit more explicit. All right, this my y and my x. The heat transfer is in the x direction. All right, it's in the x direction. If heat transfer is only in the x direction, then that means that the other two partial derivatives cannot survive. Why? No heat transfer, no q dot in y or z. Remember that if there's heat transfer, there's gonna be temperature variance, and we're dealing with a one-dimensional, one-directional transport problem. So our final equation, we've reduced our partial differential equation to an ordinary differential equation. So voila. Very good. This is for my first domain. Zoom out a bit, and I'm gonna cheat a little. I'm gonna try to be a little sneaky. What's gonna happen with the other two domains? All right, the other two domains are also steady state, and they're also 1D. There's also one-dimensional heat conduction. Okay, both of the other domains are also steady state, and there's also one-directional 1D heat conduction, right? Which means that I'm going to apply the same assumption, using the same assumptions, the steady state, and the one-dimensional heat transfer. The other two equations are just going to pop out as wait for it, as voila. Okay, sorry. Let's make sure my colors are correct. We're gonna be very picky about the colors today. Sorry. Domain 2 gives me this nice ordinary differential equation. Nice. And keep in mind, I've used the same simplifications, the same reasoning, steady state, one-dimensional heat conduction without any generation. I mean, there is no generation in this term, okay? We haven't dealt with generation yet. And lastly, domain 3. And that's just going to be the second derivative of the temperature in the third domain with respect to x is equal to 0. So now we have, let's see how far we have come. How far have we come? We have 3 second order ordinary differential equations. Okay, that's what we have so far. But in order to solve these, how many boundary conditions do I need? How many boundary conditions do I need? Okay, I need, for my first domain, I'm going to need 2 boundary conditions because it's a second order derivative. For the next one, I'm also going to need 2 boundary conditions because it's also a second order. And for my last one, I'm also going to need 2 boundary conditions because it is, as you guys have guessed it, a second order. So the boundary conditions required are 3 multiplied by 2, 6. 6 boundary conditions, ladies and gentlemen. 6 boundary conditions to solve these ordinary differential equations. Sorry, domain 1. And let's see, I'm just gonna, before I end this video, I'm just gonna integrate each of these. I'm just gonna copy them, paste them down here, and I'm just gonna integrate. I'm just gonna give you the integrated form. And I'm assuming you guys know a little bit of calculus to perform this, which means that my first ordinary differential equation is gonna become T sub 1 is equal to, let me use different colors for my constants of integration, a plus b. T2 is going to come out to be c plus d. And T3 finally is going to come out to be, alright, wait, you guys have already guessed it by now, hopefully, is E plus F. Please note that A, B, C, D, E, and F are the, you have a total of six constants of integration, which I have to solve for algebraically. 6 constants of integration, which is why I absolutely need 6 boundary conditions. 6 boundary conditions in the X domain. Alright, so there you have it, guys. Thank you very much for watching, and stay tuned for the next part of this video. Alright, thank you.